Structural fire design. The fire may destroy not only the wooden constructions but also the concrete constructions. At high temperature, the concrete loses its structural integrity. In this example, we simulate a column subjected to the standard fire. Here you can see the references to the standards where this example is described and to the standard where the standard fire temperature curve is specified. The task is to calculate the temperature dynamics. To simulate this task, I'm going to use the transient heat transfer model of QuickField, and in the end I will compare the results calculated by QuickField with the ones provided by the standard. Okay, let's start QuickField now. In QuickField, I create new problem. Column. Next. Problem type is transient heat transfer. I'm going to simulate a single cross-section of a column, so the model class is plane parallel. Length units are millimeters. Next. And here I should specify the integration time. The standard fire lasts for 1 hour, so I'm going to simulate 1 hour with the time step of 60 seconds. And the initial temperature is plus 20 degrees Celsius. Finish. On the left is the problem pane, and on the right is the geometry model editor window. Here I should draw the geometry model. I'm going to insert a rectangle with the dimensions 160 by 300 millimeters. Insert. Close. Zoom to fit. And if you take a look at the standard, you will see that in fact they simulate only a quarter of the cross-section. So let's repeat this in QuickField. I switch to insert mode and draw the line here and here. Switch to select objects mode and remove unnecessary parts. So we have a quarter of the column. Let's assign labels. So labels you can explain the geometric object's meaning and provide the physical properties. Again, use the select objects mode, click the object to select and type in the label name here. This is column. These are the axes of symmetry. At these axes we have zero heat flux. And these sides are subject to the fire. Now let's provide physical properties for these labels. Double-click the label name in the tree. For the symmetry edges, I specify zero heat flux boundary condition. For the fire, I should specify the convection boundary condition with the convection coefficient of 25. Let me check. Yes, 25. And the radiation boundary condition with the emissivity value of 0.7. 0.7. And what about the temperature? Let's take a look at another standard. This is the standard fire temperature versus time dependency. Let's copy this in QuickField. So the temperature is 345 multiplied by the logarithm of 8 multiplied by time plus 1 and plus T0, which is the initial temperature, plus 20 degrees. And time is in minutes. In QuickField, we use seconds, so time divided by the 60. And in QuickField, we use natural logarithm, so here I should divide by the logarithm of 10. And the same temperature value I use for the radiation. OK. For the column, the thermal conductivity of the concrete depends on the temperature. Here you can see the equation. In QuickField, I can specify the tabulated dependency. So here in Excel, I have prepared the table. I copy this and paste it here. Close. Both specific heat capacity and density depend on temperature. In fact, the temperaturized dynamics depends on the ratio of the thermal conductivity to the product of specific heat and the density. So it is possible to combine and pack all nonlinearity to specific heat dependency and leave the density constant value. Again, let's take a look at the standard. So you see this is the equation for the thermal conductivity. We use the same equation here in Excel. And this is the equation for the specific heat, taking that the density is a constant value, 2,300 kilograms per meter cubed. If we had a dry concrete, the dependency will be this straight line. But because of the water content in the concrete, we need to spend some energy to evaporate the water. This is called the latent heat of vaporization. Again, I used Excel to make the tabulated dependency. Here it is. I copy this and paste in QuickField. The density is to 2,300 and the specific heat. Here's the dependency. Okay. That's all for the geometry model and for the material properties. Before I can run the analysis, I should build the file implementation. Just press this button and solve the problem. It seems we have some difficulties with convergence. Let's adjust the mesh manually. I will set the spacing 10 here and at the boundary 0.5 millimeters. I have much dense mesh here. Let's again try to solve the problem. Now it works. You see at this edge we have very high temperature gradients. QuickField doesn't know this in advance, but we know, so I have specified the much denser mesh here. The problem is solved. Let's take a look at the results. Here you can see the temperature distribution. I can adjust the field picture and switch on the isotherms. Let's compare this picture with the one that we get in the standard. Now, these are the temperature distribution after 30 minutes and after 60 minutes. 900 degrees, 200 degrees. Let's see what we have here. Base 0 with a step of 100 degrees. And for the color map, I set 900, 10 steps. So this boundary is 900 and this is 200. You can get the exact values using the local values tool. Just click this point, 200. Click this point, 900. So this corresponds to the temperature distribution at our 60 minutes since the fire started. Now let's change the time step to 1800. Now this is the temperature distribution at 30 minutes. Again, let's check the temperatures. Click here, this is 100 degrees Celsius, and these should be 800. Click here, 800. If you search for the structural file design on our website, you will find the example page. Here you can read about problem setup, browse the solution section, take a look at the result pictures, and download the simulation files. Simulation files may be opened and the results may be viewed using any QuickField edition, including QuickField Student Edition, that you can download from our website for free.